All right, today we are diving deep into a hidden universe that's all around us, and even inside us, the world of bacteria. It operates on a scale you can't even see, but it affects literally everything. We're going to look at a totally new way scientists are starting to understand, and yeah, even predict how these tiny, super complex communities actually work.
It all really boils down to what sounds like a simple question. When a bacterium is floating around with a bunch of different food options, how in the world does it decide what to eat? Is it just chaos, a total free-for-all, or is there some kind of master plan at play?
Well, to get to the bottom of this, scientists basically created what you could call a microbial marketplace. It's a controlled space where they can actually watch all these little interactions play out.
Now, when I say marketplace, you've got to understand the scale here. We're talking about a synthetic community in a lab, and even in this simplified version, the numbers are just staggering. You have trillions of bacteria making critical choices every single second. It's exactly why you need some serious modeling power to make any sense of it.
So, how did scientists used to model this? Well, for a long time, the methods were, let's just say, a bit basic. It became pretty obvious that to really understand what was going on, a much smarter strategy was needed. And here's where the big shift happens. The old way, the kinetic model, pretty much treated bacteria like simple little machines that are just always on, gobbling up whatever's there. But the new cybernetic model, it's a whole different ballgame. It sees bacteria as tiny, intelligent factories that are constantly making the best possible choices to grow and be more efficient. It's a complete change in how we think about them.
Okay, so if a bacterium is a smart factory, it has to have some rules of operation, right? Well, the cybernetic model says its whole strategy is basically run by two key variables that guide every single move it makes. So the first rule is all about the variable U. The best way to think about this is like the factory's HR department making a hiring decision. When a new type of food shows up, the bacterium has to decide if it's worth the energy to build new workers, which are enzymes, to process it. It's a strategic call about investing in new skills.
And the second rule, that's governed by the variable V. Now, if U is about hiring, V is the daily work order. The factory looks at all the workers, the enzymes it already has on the payroll, and decides which ones to put on the assembly line for the most profitable job at that exact moment. This is all about using what you've got to get the biggest payoff, right now.
Okay, so those are the rules for one single factory. Pretty neat. But the real power, the real breakthrough is when you scale that logic up from just one bacterium to an entire bustling microbial community.
And the scientists built this model in a really logical way, just piece by piece. First, they start super simple. One kind of bacteria, one kind of food. Easy enough. Then, they add a little complexity. One bacteria, but with a whole menu of food to choose from. And finally, they simulate the whole shebang. Multiple species, all with different tastes, all competing for the same stuff. You can see how the complexity just builds from these simple rules.
And this is where it gets really fascinating. Because once you have this full marketplace model running, you can start to explore the most fundamental strategies bacteria use to survive. Are they selfish competitors, or are they team players? The model basically lets you test two different scenarios. In the selfish mode, every single species makes choices only to maximize its own personal growth. Who cares about the neighbors? But then, you can flip a switch to the teamwork mode, where each species makes choices that are best for the growth and success of the entire community. That first competitive idea is captured perfectly in this quote from the research. The default setting, you could say, is that every species is in it for itself. It's going to invest its precious resources with just one goal, maximizing its own biomass, its own growth. So a computer model is one thing, right? It's clean, it's elegant, but it's only as good as the data you put into it. So how do scientists actually connect the slick digital factory to the messy, complicated reality of what bacteria are actually eating out there?
I mean, that's the critical question, isn't it? Real-world food for bacteria, things like plant fibers, they aren't simple sugars. They're this tangled, complex mess of all kinds of molecules. How can the model possibly know what it's even supposed to be processing?
Well, the answer lies in a really powerful analysis tool. There's this technique, PMA-GCMS, that basically acts as a translator. It takes something complex, like that plant fiber, and it breaks down its chemical structure, identifying all the specific bonds between the molecules. It's like creating a super detailed nutritional label that the computer model can actually read. This turns a real-world mess into precise data, which makes a simulation so much more powerful.
And that really brings us to the biggest takeaway of all. This cybernetic model isn't just a better way to describe what bacteria are doing. No, it's a massive leap forward. It allows scientists to start predicting their collective behavior. We can actually run simulations now to see how an entire community of microbes might respond if we change their diet or their environment. So we end on this pretty amazing thought. If we can get really good at predicting how these huge invisible communities work, what kind of doors does that open up? Could we design a gut microbiome for perfect health? Could we engineer bacteria in the soil for more sustainable farming? Being able to model this smart factory gives us an incredible new tool to maybe, just maybe, start shaping the microscopic world around us.